Jangan mula je.
Dah.
Aku tak.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. Good morning, salam sejahtera to everyone. Would anyone respond whether you receive my voice or notes and
Morning,
also my
Doctor.
slide?
Can hear you loud and clear.
Yes, thank you. Thank you very much for response. Thank you again. Shukran. We can meet again on the 14th of November 2021. And also on the 9th of Rabiul Akhir 1442 Hijriah. And our class will start at 8 to 10 for 2 hours class. We are going to continue the last thing that we discussed earlier was about the effect on gyroscopic couples. We already completed this one, so you can turn your notes or your book perhaps on page 100 and something. 100 and let me check here. You can turn to page on 100 and where are you? 100 and those who have book with you can turn to page 161. 161. Here also, yeah, 161. Okay. As we all exposed last weeks, we've been talking about the principle. Then we're going to talk. We have also been talking about the use of gyroscopics, and we explore the spatial application on the auto and shaft. Then we move to the aircraft. As for today, we're going to look for naval ship, speedboats, so on and so forth. Anything that the sea transportation, yeah, sea transportation. Okay. So you can turn to page I believe 100 and something. So I can quickly move to this one. We completed this one. We completed alhamdulillah this one. We're going to look at here motion of airplane. We completed alhamdulillah. We're going to move on. Example, we done the example. This one, yeah, naval ship. And as usual, I did, as I mentioned earlier, yeah, the principle meaning that general equation from the from the equation that if I can write something here. So the principle is basically the equation used in solving the problem. Typically, have earlier was the m equal to I dot this one the precession cos the this one spin cos precision is exactly the same, and toward that the omega is basically this one. Yeah, this one is omega is for spinning velocity or spinning speed. It comes from the propeller, the device or the body or the thing that make the ship to move or steering. So it comes from the propeller or turbines and so forth, basically on propeller. And the precision will become on the motion where you have the turn to left, turn to right. If I can on my video here, okay, you have to turn to this one left, to my left, yeah, my left. This is the right, and you have diving, there's no diving, there's no such diving. We call it as pitching down, where you found that the bow or the front end will be descending, it's pitching down. And if you go back to the aircraft, it's very similar to diving. Then you have this one, yeah. You have the climbing, there's no climbing, such climbing motion on ship. We call it the pitching up. You have pitching, it's not pinching, yeah, it's a pitching, pitching down when the bow will be descending. The other one is pitching up when the bow will be ascending. Descending means the bow will be pointing downward, ascending means the bow will be pointing upward. Okay, and of course, you also have roll clockwise or my clockwise. It's not your clockwise now, my clockwise. The other one is roll counterclockwise. So it is not the whole rolls where you have 360 degrees or 180 degrees, which will be experienced as a Titanic. No, it's basically a very small or very minor roll. But the roll will be on clockwise or anti-clockwise or counterclockwise. Okay. So don't worry about the what do you call it, yeah, the marine terminology as such as ports, as such as starboards, or perhaps bow, yeah, or stern perhaps. So we are going to use as the standard marine terminology as port, but we are going to put a bracket to ensure that everyone understand what port means, starboard, so on and so forth. Okay. And in addition to that, the speed of the ship typically on nauticals, isn't it? Or we are going to put a what they call it, the factor to convert the nautical mile, perhaps, is equivalent to how many kilometer per hour. So don't worry about all that kind of terminology in marine. So guys from marine, from the it's not very SKMO, I presume, very much keen to use all this, terminology. Yeah. Okay, this is naval ship again. You have this one, as I mentioned earlier, steering. The steering could have this turn to left or turn to right, or right turn and left turn. Pitching, as I mentioned earlier, the bow be pointing upward. We call it pitching upward. The bow will be pointing downward. This is the bow, yeah, will be pitching downward. Rolling typically clockwise and counterclockwise, and very small roll. In particularly, they mention about the angle, letter one. Okay. Okay, now let us pick up one example, or perhaps one what do you call it, case where we can basically define what are the things they're going to look for today. Let me allow me to open one of my files so that I can write something on it. So I'm going to put on my blank template, so that you can see, or I can explain further. Okay, I will again, I have problem with the pull down menu here. The pull down menu not allow me to use yeah, okay, now pick up one. So let's say you have don't bother to copy. Yeah, you have this one in your note. I provide you both. One will be in your book and the other one is in your notes. Consider the ship taking right turn. Okay, right turn, and the rotor rotate with clockwise direction. So rotor rotate clockwise. Rotor could be the propeller, for example. Yeah, this one clockwise direction, viewed from where? Viewed from stern or rear end. This one is rear end. They will provide you this one, either look or view from stern or view from bow. So basically, your eyes is here, and the vehicle, the ship will be pointing upward, moving forward, and it also turn to right, turn to the right. Sorry, this is left, this is right. So as you are looking or viewing the rotor rotating clockwise from here, this is clockwise, yeah, clockwise, isn't it? So clockwise is simply that this is clockwise, my clockwise, this is my counterclockwise. So this clockwise. So as you have this clockwise, so the omega or perhaps the spin velocity will be pointing that way, right? And the ship now is, make a left turn. This is the left turn, this one is the right turn. So left turn, so you will have this one be pointing upward or pointing downward. So if you have a right turn, be pointing downward. You have a left turn pointing upward. So this is what we call a thumb rule. Start all with thumb rule. So left, right turn pointing downward. So this precession velocity pointing downward. Then you start constructing the what the the what do you call it, the gyroscopic vector diagram. So if I can do this one at a time, just to ensure you really understand about this one. So you have a boat here, propeller, ship or boat, yeah. So your eyes is here. This one you view at one point. This one is the stern. This one is clockwise. So as you move clockwise, you'll be pointing toward here. Then it turn to right, pointing downward. So then if I can put another color here, so that very easy for you to distinguish or to determine. Yeah, this one is this one is turn to right. So when you construct the gyroscopic vector diagram, you'll be getting the omega, the spin velocity, you'll be getting the precession velocity, and you have two choices. Either you want to construct with 2D or 3D, it doesn't matter. It's up to you to decide which you feel that very convenient to you. So you start to use thumb rule. Sorry, right hand framing rule. So this is the right hand framing rule, yeah. So to remember this one is spin, this one be your precession, this one be your couple. So you will have as such, isn't it? Put your hand here. You put your hand on the drawing, so you find that this one is spin, this one the precession, this one will be the what do you call it, the couple. So let me close this one. Okay, so you have couple be pointing inward of your screen, isn't it? Couple be pointing inward your screen. So you have this one. So you have, so it's not inward, outward. This one is M active, outward of your screen. So, and this is not our concern, as I mentioned earlier, isn't it? So many times I did mention this one, yeah. So you have this one, the M reactive, which always M reactive, which always your concern talking about the effects. Okay, I'm not going to talk about the effect from the structure because we did it so many times, yeah. The structure will be basically from this equation. Remember, I dot this one be the spin cross precession, isn't it? So I actually mr square can also be written I also in the term of mk square, depending on which parameter being given. And the other one is the omega is basically on the propeller speed. So the propeller speed or propeller operation velocity. So you have this one 2 pi n divided by 60. And again, yeah, this one, remember, the precession will be the velocity at that particular instant divided by the rule. Rule will be the radius of curvature, while the ship turn to left or turn to right, isn't it? So you have this one. So you can take this one, put it in the equation. So you'll be getting this m. Okay, and this m is belong to active and also belong to reactive. Okay, so that one is I'm not going to talk about that in detail. I'm going to concern, or perhaps I'm going to detail on the effect on body. So effect on structure, as what we've done earlier from the first part of our lecture. So on structure, for example, the propeller now, and the propeller here supported by bearing, for example. This one is the front view. Okay. Then when you concern about the reactive, you take the reactive, which is now inward whiteboard. Sorry, it's not whiteboard, inward screen. Inward screen, be rotating clockwise from your seat. So you have as such, this one is clockwise. Inward screen, clockwise, isn't it? So you take this one and put it here, M reactive. Then you know this one will be the F due to gyro, perhaps. You put another one, this one also F due to gyro. So this F due to gyro is on structure. And I'm not going to talk this one in detail because we've done this one so many times. Yeah? On body, for example, yeah, on body, or you can put it on ship, for example, on body or on ship. The effect will be, if this one is the ship, again, You go back to the gyroscopic vector diagram, and you take this one, focus on the reactive, you put on the ship. Ship will be, this one is M reactive. So you found that there must be one force acting, sorry, you found that there must be one force acting downward to comply the directional rotation, and one force acting upward. This one be what? This one be pointing upward, this one be pointing down, and put it there, also F. So the bow will be pointing upward. So the stern will be pointing downward, or perhaps deep. Huh? Okay. If you go back to the equation, you go back to this one, you found as what you have here. Yep. How come this one is different? Let me check. Reactive on. Oh, okay, okay. I'm wrong here. I'm taking the wrong direction. That is your notes is correct. I'm taking the wrong direction of the M reactive. Sorry for that. Yeah, it's supposed to be this one. It is pointing or rotating clockwise, so it's supposed to be rotating clockwise in such manner. Will be this one. That is correct. Practice. I take the wrong direction. Then you have one force acting upward, one force acting downward. That's what you have in your notes. This one. And you can put it as raise the stern. Why the raise? Because it's pointing upward. And the lower the bow or dip the bow. This one. Why? Because it's pointing downward. If you forget about raise the stern and also lower the bow, you just put, the stern will be pointing, or the rear end pointing upward. Then the the front end be pointing downward. Okay, that's all do, inshallah. Huh? Okay. We are going to look for another one. Yeah, let assume that the ship now make a left turn. Okay, make a left turn. I'm not going to go in detail again on constructing this one is 3D, constructing 2D. I think at this point we already know what is the difference between 2D and also 3D. So you pick one, whether you want to draw 2D or 3D, which will feel that convenient to you. Yeah. Okay. The other one will be, you have left turn now. Okay, left turn. We are basically talking the same shape. This one, you are here. This one is looking at stern clockwise, and this one don't change anything, which is spin will be pointing, pointing towards or pointing uh, on right side. Yeah. So it is turn to left now. Turn to left. So this one, as mentioned earlier, turn to right, direction of vector, direction of rotation. This one is direction of vector, direction of vector, direction of rotation. So it be pointing upward to ensure that the ship now make a left turn. So it be pointing upward. So you have that one. So if you construct the just copy vector diagram again, you'll be getting this one be spin just now. This one will be the precession. And if you put your fingers, yeah, on the line or on the skin, you find that this one will be the the precession spin. Then the moment or the couple will be pointing inward the screen. So this one is the moment, and this one is the active. And again, it is not our concern. Our concern is this one is the M reactive. Just remember that or any effect on the structure or also on body, our concern is to look, or our interest is to look for the M reactive. A structure as usual. I'm not going to talk about structure again. I'm going to talk about on ship now. On ship or on body. Sometimes put it on body. So what you have now, this is the ship. Then you are picking up the M reactive. That reactive will be pointing to you. Be rotating what? Counterclockwise. Rotating counterclockwise. So you put it there. Okay, rotating M reactive. So you have one force pointing downward, which is F. The other force pointing upwards. So where you have the stern be pointing downward and the bow be pointing upward. And what will be the magnitude for the force? We do not know until or unless we know what will be the length of the ship. But very seldom that the equation when asking about what is the force not on body. Typically, our concern, because we are an engineer, concern about force on bearing, on bolt and nut, on bracket, for example, yeah, or perhaps on shaft. What will be the force on shaft? Huh? So if you go back to the actual thing, this one is very nice for you to look at. You found as this one pointing downward, the other one pointing upward, and we know this one as raise the bow. Raise the bow is called pointing upward. This one lower the stern because it's pointing downward. Okay, so that one is, and basically in conclusion, yeah, whatever you have for turn to left and turn right is basically the opposite answer. Okay, so do not memorize this all thing. What you need is to understand how to go about it. Yeah? Let's now focus on the other one, naval ship on pitching. As I mentioned earlier, pitching is where the phenomena when you found that the front end here, bow, be pointing upward, we call it pitching upward or ascending, A-S-C-E-N-D-I-N, ascending. The other one is the bow again, it be pointing downward. What you found is a descending, D-E-C-E-N-D-I-N-G, descending. Okay, ascending and also descending. Okay. So how are we going to look this one? I'm going to explain a bit about this one. If you know that the ship, this one, yeah, the ship, you know this one pointing upward, pointing upward. So this is the level, this one is the level. So this one is the extreme position. Of course, when this one is the above level, we found this one extreme, maximum, or perhaps the highest. Isn't it? This one also extreme, in position. This one be the lowest. How do you experience on board here, for example? Okay, as you all know that when you are on board, for example, typically when you are a very small boat, for example, yeah, if you take a cruise, yeah, or a big ship or naval ship, for example, you don't feel this one. But you take a very small boat, and when the boat hit the, the wave, yeah, the wave will be typically constructing or perhaps assuming that the wave will be on simple harmonic motion. Because if you don't assume that the wave will be in the form of simple motion, it's very difficult for us to calculate what be the wave equation. So we are going to assume that the wave is very smooth, constructing or presenting the simple harmonic motion. Okay, the simple motion basically come from the sine and cos. Okay, so we pick up here, then the wave is as such here, very nice wave. And of course, in the real thing or real, phenomena, you find that you have a very rough sea. You will have a very random wave, position which you cannot define. So in mathematics, if you want to do something and you want to calculate something, you have to make an assumption. Okay, that is why you have to look for the extreme position highest and extreme position lowest. Assuming this one is simple harmonic motion, where you found this one, it will be what basically very good or very nice curve. This one be sine or cosine curve. Class, I construct this one sine or cosine.
Sine, doctor.
Sine, yeah, because sine 0 equal to 0. Okay, so assuming this one, yeah, this one will be at here, for example, so it be pointing upward. So meaning to say that in the actual thing on practical, so the ship will be hitting a wave and climb up to the highest crest, isn't it? Because waves have crest and valley. So this one is the crest, C-E-R-S-T. This one is valley. Okay, up to highest point or crest. Then at the highest point where you found that the velocity becomes 0 at that particular instant, then it will fall down to the valley. And if you found that they will be keeping climbing and climbing, so there is no the velocity is not reaches the maximum yet. So to ensure that they go back to the valley, so the velocity at that particular instant must be at maximum. So this one, we consider this one at maximum. So at maximum, the velocity become 0. For example, of course, it will not pause at that point. It go back to the valley. So, for example, yeah, if you throw a ball in the air, you throw the ball in the air upward, the ball will keep climbing, climbing, and climbing until a certain period of time. It will stop a bit, isn't it? Then we'll go back and reach ground. So, when the ball will not reach at the maximum speed, which is zero now, it will keep climbing and climbing and climbing. Correct or not? That is very logic. You learn this one in dynamics so many times earlier, isn't it? On projectile, for example. Okay. So likewise, this one. So at maximum, so the same thing at valley, you will have the maximum. So while the ship climbing the wave, it will reach the crest, and while the fall down go to the valley, also will reach at the maximum point. Okay. So now what you have is you will have this one, what we call as theta. So this theta is the angular, if the angular spelling is 1g, yeah, is the angular displacement. Angular displacement. So let theta is equal to angular displacement. Angular displacement. Theta. Climbing, 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 and from 0 degrees up to here, isn't it? So it will be at maximum. So theta now is equal to theta naught. This one will be sine omega t. Because we start with sine. Can we start at cos? Yes. So it depends. You can start with cos, you can also start with sine, doesn't matter. So this one will be what? This one is what we call angular displacement with respect to time. This one is angular displacement, which is at the stationary. This one is angular displacement with respect to time. Right? So then it start what? D theta by dt, which give you theta dot, which will give you this one is omega theta naught cos omega. This one now is angular one. First is angular displacement. You will have angular velocity. Also, the displacement with respect to time will give you velocity, velocity. Then we stick climbing, climbing, climbing until it reaches maximum. So we have t 2 theta d 2 theta by dt power of 2 theta double dot, becoming negative omega square theta sine omega t. So this one is the acceleration. So we have displacement, velocity, and acceleration. Okay. So as I mentioned earlier, we are concerned now is to look one. This one is the wave. We are going to look for wave equation. Wave equation. So this is the wave equation. This is all the wave equation. This one, yeah, wave equation. Okay. So because we concerned about the velocity, yeah, so we're going to talk about this one. So because our concern is on velocity, so we're going to talk about this one. Yeah. Velocity. So, and you have the theta dot, you will have omega theta naught. This will be cos omega t. The theta naught is the what? Is the displacement. Okay, theta naught is displacement. Perhaps if I can show you this one, theta naught be here. This one all theta naught. Displacement, displacement, displacement. Angular displacement, of course, yeah. So at maximum, as I mentioned earlier, what happened to the maximum? Yeah, this one becoming, cos becoming. What happened when at maximum? This one cos omega t becoming. Anyone? Yes. Anyone?
Zero, Doctor.
The cos it cannot be zero. It must be one, isn't it? Cos theta equal to one. But how to ensure cos theta become one? You have to look for theta equal to zero. Correct or not? It's not zero, it's 180, so on and so forth. Multiple by 90, 90, 90. So at maximum, we have to ensure this one. Yeah, we have to ensure at one. So this one now at maximum. So therefore, you found that the theta dot is equal to omega theta. This one put it in maximum. This one also put it at maximum. This one all at maximum. Okay. So remember, yeah, this
Sorry,
one.
kenapa dia satu?
Sorry,
Why the cos omega theta is 1? Sorry.
why we?
Why the cos omega theta, cos omega t is 1?
Because we want to look at maximum. To look at cost. This is
Oh,
cost, correct? Yes or no?
yes.
So cost maximum will be at 180 degrees.
Oh,
Yeah, isn't it? So as I mentioned earlier, at maximum, what happened to the maximum? Maximum meaning what? There is no changes in velocity. It will stop a bit, then it will be fall down following the wave. It will not stop. You will not pause. Yeah, pause a bit, meaning that there is time still running. But we are in engineering, we pause a bit, but time still running. Pause meaning we want to look for the maximum. Okay. Okay, like you are, for example, yeah, you are taking a vibration measurement on a structure. When you're taking vibration measurement, you cannot take as what in 1 minute, sorry, in 1 second or 2 seconds. You need to give the structure to what? To stabilize the speed, one, to stabilize the vibration amplitude. Allow it to become 50 seconds, 1 minute, 5. Then you only take measurement. If you suddenly pick up, the measurement, it will be very wrong because while turning on the machine or turning on the motor, it will still speeding up. It will not reach the maximum speed. Okay. Okay, now. So as you have this one, remember this one. But this t theta dot, yeah, this one is maximum, yeah. How do you know it's maximum? The question will ask you. This one, sorry, the question will tell you to do so. This one is also maximum. This one is theta dot. This is very important, class. This one is the precession because due to wave, this one is precession. You change maximum equal to omega maximum theta dot, and you have another equation, m equal to I dot omega cross precession. This one okay, correct? But this one maximum, yeah, this one and this one is not the same. It's not the same. Remember that this omega max, this one, yeah, due to with due to what? With this omega due to propeller, or spin. So you, even though you have the omega, so it would very different compared to what we have. This one, this omega, yeah, this omega, what you have is the omega equal to 2 pi n by 60. This omega, no, this one is from wave, so the equation must provide you again a wave profile. This is what we call wave profile. How is it? They must provide you time, predict t. If it's not provide you predict, it will provide you angle, for example, angle. So you have omega is equal to, what is the equation for omega? Anyone know? Class?
2 pi over t.
Pi?
2 pi
2
over
pi
t.
over t, correct. Where is t? T is this one. So you have the omega. So it is not equal to omega. You have this one for spin, where you have 2 pi by n by 60. It's not equal, yeah? This one must be from the wave profile. Even you have the same notation, but you have a different definition of the things. So any question? So the question will provide you this one. They must provide you the wave profile. If they will not provide the wave profile in terms of diagram or figure, they will mentioning about information in sentences. Okay. So we go back to here. When you understand this one, when you go back here. So in conclusion, if I may say, for example, so you have m equal to I, this one is omega, this one be precession. So this one no big deal, no big deal, no big deal. This one now is turned up to become at maximum. This one be what? Omega maximum. This one is theta. So the omega now be from the profile. This one, remember, from the wave profile. And this one will be the amplitudes. or perhaps we call it the angular displacement. Angular displacement. Okay. Okay, now let's now pick up one example. Before we go this one, I want you to understand how to use it. So pick up this one. For example, look at here, example. Look at here, this one, yeah? The ship is pitching and the boat is descending. What does it mean? It's pitching. It's pitching down. What? With the maximum velocity. Maximum velocity. What does it mean? Maximum velocity meaning that your cos theta become 1. Your sin theta also become 1. If you are start with cos, it becomes sin. Yeah. The pitching is simple harmonic motion. They must provide you this one, otherwise you cannot calculate. This simple motion is due to wave profile, and the predicts is 18 seconds. 18 seconds. So what is the predict? The predict will be this one. The periodics T. And the total angular movement between the extreme position is 12. What is that? That is I want you to understand this one. This one, remember this one extreme, this one's level. What does the question tell us? 12 degrees extreme between extreme position. So this one is extreme, remember? So this one will be 12 degrees. But the question also mentioned about descending. So we are basically talking about this one below the level. This one is pitching down. So your equation, this one is equal, sorry. So your equation, again, this one, mi, this one, no big deal. Focusing on this one. So your equation now is equal to what just now? So of course you have to start with, you have to start with, as I mentioned earlier, you need to start with theta length, theta equal to theta naught sine omega t. Then theta dot equal to omega theta naught, this one cos omega t. Theta double dot, because this one is all wave equation, square theta naught sine omega t. So we focus this one because we are talking velocity. So put it here at maximum. You found that theta dot is basically maximum is omega maximum theta naught, where you found that the cos omega t equal to 1 when put it there theta equal to 0. So that no, you get marked for that, yeah, you get marked for that. Then you use this one. So therefore, the precession, because you're talking about the profile of the ship, profile of the wave equal to omega. This one put it at maximum. This one theta naught. This one, of course, they provide, isn't it? They provide you as omega equal to 2 pi by t, where your t is equal to 18 seconds. This one done. But the other part is theta. Remember this one? I did mention about displacement. This one is the angular displacement.
Sorry.
Yes.
Can I ask, the education give the 12 value 12 for angular displacement? Is it given?
Angular displacement.
Yeah, with just now yang ada 12 degree tu. Yang
Yeah. I'm going to talk this one. You hold on a bit. This one. I'm in the middle of explaining the angular displacement. Okay, you hold on a bit, yeah? Hold your breath first, yeah? Hold your breath first. So I'm going to go back to here. So what is mentioned? Extreme position is 12 degrees. So you have to understand what is extreme. So extreme position 12 degrees. So your concern is only for what? Pitching down. This is your concern, isn't it? Pitching down. So it is not basically 6 degrees. It's it's not basically 12 degrees, basically 6 degrees positive, 6 degrees negative. Isn't it? Then this one theta dot is basically 6 degrees. But of course, you need to convert this one to become radian, where you have the 6 degrees divided by 180. Convert from degree to radian. You cannot take this one 12 degrees because why? Because they measure the whole thing from extreme to extreme. But if you measure from the level to the extreme, then you take 12. So you have to look the question very, very careful. or you have to read the equation very, very careful. Okay. When does the negative, vanish? Because we are talking about what? Pitching down. So pitching down is negative. Another negative, it basically vanish. Okay, I'm going to do this one, the effect on structure. Sorry, the effect on shape. Yeah. So pitching up. Pitching up. Okay, pitching up. Look at here, pitching up. You're still viewing from one end. This one is your clockwise just now. You will have the omega. Correct. Now pitching up. So pitching up simply means that this, the bow now pointing upward. The bow be pointing upward. So you have this one. So bow pointing upward. So your thumb be pointing. My thumb be pointing to me. It's supposed to be that way, isn't it? Pitching up. So what does this mean? So I put it here as it will become out here. Precession. If I can share with you here, yeah, for example, or perhaps I can draw another one. I will have as such, and this one be my precession. This one is pitching up. Then you have a spin, the spin, precession, then your couples. Couple pointing upward, couple pointing upward. And again, this is the M active. This is not our concern. Our concern is to look at the M reactive, reactive. This is the effects. If you put this one on chip, for example, yeah, put this one on chip. Let's say this is the chip. And I share another color. So look at here, pointing downward, correct? So be pointing downward. So an M reactive. So from top view, if you look at from top, for example, plan view, you have isn't it? From plan view, what you have is pointing downward. So it be, am I correct or not? Correct or not? This one is side view, and make it turn to plan view. This one is front view, for example, or side view, yeah, side view. Correct or not? Yes or no? Yes or no, class?
Yes,
Anyone? Okay, now, so what happened to the structure? What happened to the shape now? So you push that way to comply this one, yeah, F will be pushed this one. So while pitching up, so the shape will be what? Pushed toward right, isn't it? So if you go back to the answer here, you will have as such. The tendency to move ship towards starboard. Don't forget about starboard, put it the right side. What happened to this? What happened to the propeller, for example? If this one be supported by propeller, remember? This one is bearing, for example, toe bearing. So what happened to the propeller? Because it occurring on the surface, you will have shear force. You will have shear. Okay. Okay, pitching down is the same thing, yeah. Opposite what you have in pitching upward. So now the bow be pointing downward. As the bow pointing downward, so look at the pitching down. So the bow will be pointing downward. So your precision be pointing your screen. So as the pointing your precision be pointing a screen. So what you have is you will have as such. Or if I can draw 3D, for example, for pitching down. Spin. Now pitching down. So spin your precision pointing up, pointing inward screen. This one is the precision. So spin. This one be precision. This one be couple pointing down. The couple be pointing downward. So put it here, couple pointing downward. Again, it is the it is the active. It is the active. This one is the active. And again, this is now consent. You will have as such M reactive. So what happened to the structure or what happened to the body? So if this one is the ship, for example, if you look at from top, you find that this one, yeah, this one will be pointing upward. This one will be pointing upward. M reactive. So if you're looking from top, so you will have as such. You will have okay, you put it here and put it on ship, so you'll be rotating clockwise from your seat. M M reactive. Oh, pointing outward. So sorry, the other way around. I sometimes I put wrong direction. Put it here, so you're pointing here. It's correct. M reactive. So what happened to the ship? So it will be pushed that way for F and push the other one that way. So to comply the direction rotation. So what happened to the ship now? The stern will be pushing that way. The bow, the bow will be pointing that way, or perhaps it will be toward left. It will be pushing toward left. Look at here, pushing toward left, toward port or left side. So please do not memorize this one. Remember, do not memorize this one. This one is when what? When you are weaving the propeller from stern, and this one rotating clockwise. If rotating counterclockwise, you'll be getting some of the results. Okay, do not memorize whatever you discuss here. So understand how the thing or how it is go about. Okay, now any question before we move to the next one? The last one is coding.
Doctor, can I ask
Yes,
for
yes,
the
please.
data note, why we use 6/180 degree?
Okay. Again, yeah. This is the ship. Level. This one is 12 degrees just now. Extreme. So we have +6, -6 degrees, this degrees. Okay, your question is why, yeah? So now you have this theta naught is equal to 6 degrees. Remember, this theta must be in radian. Must be in radian. So you convert from degrees to radian. Isn't it? Converting from degrees to radian is theta is equal to 6 multiplied by 2 pi by 360. Am I correct or not?
Okay, understand now, doctor.
Okay.
Understand. Thank you,
So
doctor.
I just simplified that with t pi by 180 to convert. This one is basically conversion from degree to radians. Am I answering your question?
Yes, doctor. Yes.
Okay. Okay, any other question before we move to the next one? This one, rolling. Okay, the rolling position or the rolling motion is basically have two, yeah. One be rolling. If you are looking from stern, for example, you have this one roll clockwise, this one roll counterclockwise. Okay, so if, for example, if they do not mention about roll clockwise or counterclockwise, you need to do both. Otherwise, do once only. So assuming this one roll clockwise, for example, so what does it mean? It simply means that you have what? You have spin, and you also have this one precession. And this one, what you have is this one, you will have I cross I equal to 0, isn't it? You will have as such this one, for example, or you will have this one. So whatever you calculated earlier, I equal to M equal to I dot precession and the spin and precession, this one now becoming 0 when you deal with vectors. And the result will be as this one. So it will be the result. So no effect on gyroscopic when the ship will be experiencing roll clockwise. So finally, before we move to the example, you have as such, yeah. This one is if you move from this one, for example. So this one is what? Turn to left or turn to right? It's turn to what? Turn to left. Correct or not? This one, turn to left or turn to right? Toward you. Tell me. This one turn to what? Turn to. Is it right or left? Again.
Left, doctor.
Right or left?
If,
Turn to.
left.
Is it correct?
If toward me is left.
So if you are here, from here toward you. So left or right?
Left.
Correct? Sure, is sure?
You mean I see in front of it or from behind of
No,
it?
no, you are here. From here, you are here. This is you.
Oh,
She will
if I
travel.
that
Then
if
basically,
right.
yes. That's what I mentioned. Yeah, if this one from here is correct, but when you from here, so you turn to left, right. Yeah, so you have to, have a very good in visualize things. This one is what roll clockwise or counterclockwise. When you look from stern, it roll what? It roll counterclockwise. This one roll counterclockwise, isn't it? But when you look, this one will roll clockwise. So it depending on where you view the ship. This one, when you view from this one will be pointing upward. This one is climbing. Oh, sorry, climbing is not pitching up. When the boat is ascending, this one you look at here, the boat will be descending, will be pitching down. This one the same thing. Yeah? This one is pitching up. So these are all, a motion on naval ship. That is why in solving the problem in naval ship, they provide you where you are going to look on the ship. So if it will not provide you anything about viewing position, you have to do your own reference points. Okay, I'm going to do this one very quickly because you have the solution with you. You have solution with you. So I'm not going to do this one in detail. I'm going to read and then go to the solution. You can turn to page 180. Okay, I'm going to read the video. So you have what you have here. You have the bind rotor 7,000 kg, weight of the whole thing, radius of gyration 60 cm. This one to provide you, remember, I equal to mk square. And it rotate, it meaning that the turbine rotating with the speed of 1,800 RPM. So this one be your spin velocity. Look at here. They provide you magnitude, they provide you where you want to view, isn't it? From stern. So if this one not provided, you have to make your own assumption. Determine the gyroscopic effect on the following cases. One, the ship traveling with a speed of 60 km per hour, steer to left in a curve of this one. So this one is radius of curvature. This one is the velocity at particular instant. This one is your motion. Okay, if your equation is m equal to I dot omega, this one the precession, this one will be remain constant, will not change anything because you are using and applying or you are traveling with the same rotor. So this one keep changes depending on v and also depending on rho. So this one you calculate once only. This one you calculate once only. Okay. For number 2, if the ship is pitching and the boat is ascending, the boat is descending, the boat pointing downward with the maximum velocity as I mentioned earlier. The pitching is simple on the motion, trading time 18, total angular movement. Look at this one, read very careful. The total angular movement between the extreme is 12. So meaning that you have positive 6 and negative 6. You add up together become 12. From level, of course. Number 3 now, what you have is number 3 now, if the ship roll and it do not mention but roll clockwise or counterclockwise, this one clockwise and counterclockwise, do both. At certain instant, the angular velocity is pi radian per second, clockwise direction. So they provide you so only one. So clockwise when looking from stern. So in each case, determine the magnitude of gyroscopic couple and explain clearly the direction in which ship tend to move as a result of gyroscopic action. As a result of the gyroscopic action, meaning effects. Okay. Okay, now I'm going to move to this one. Your solution. Very quick one, yeah. The next example will be done when we completed the whole thing. Yeah? So look at here how the solution explained here. So first is due to the motion, yeah, left turn. Then you equation calculate this one once because you'll be using this one over and over. So calculate this one once. Calculate once. Then this one keep changing depending on this one keep changes. Depend on the velocity and also rho. You'll be getting as this one. Same results, different in direction, in opposite direction. Okay, then we start construct. First is the equation, then we start construct the scopic vector. How is it? The ship. The ship is here, for example. So what does it tells you? It simply tells you that clockwise when looking from stern. Okay, clockwise from looking from stern. This one is stern, this one is clockwise. So I change another color so that you can differentiate. So clockwise. So it will pointing down. Sorry, it will pointing that way toward my right. So this one is the spin. Then pitching up, pitching down. It is now. This is now turn to left. Pitching up, pitching down. Turn to left, turn to right. Turn to left, pointing upward. So pointing upward, turn to left. Then I move here to do the gyroscopic vector diagram. Spin, as you have here, this one. This one is the precession. This one will be one. When you have this one, so it will be pointing inward. So this one is active. This one will be reactive. And this is the effect. So you take this one, put on the ship. Put on the ship. This one is equal to here. From to the gyroscopic vector diagram. Okay. Then what happened? To comply this one will be your side view. You look at from that point. So one force acting upward, one force acting down. And we do not know how much the force acting on the body. Okay. You can also put it here, doesn't matter. Yeah. If you like, you can also put it here. But very different, very difficult to me, for me to explain to you. Very difficult in that point of view. So I will prefer to view directly perpendicular to the spin. Easy for me to explain. And you found this one. What happened to the structure now, or what happened to the body now? The bow will be pointing upward. The stern will be pointing downwards. Okay, as I mentioned here, raise the bow and lower the stern. It's not very difficult, isn't it? It's not very difficult. Eh? Okay, and again, do not memorize the whole things. Eh? Okay, look at here. The bow ascending, pitching down, and extreme position 12 degrees. You have 6 degrees up, 6 degrees down below the level. So they provide you this one. If they not provide you, they must provide you the T, this one. Otherwise, you cannot solve. But sometimes it will not provide the T, they provide the length, the, what they call it, yeah? Wavelength. Wavelength. They will provide the wavelength. Again, you have to convert the wavelength to become some other form of information. Yeah. So you do this one do not change. This one calculate one, as I mentioned earlier. So the only difference now is this one. But please do not to forget the what? This one. From the beginning, then you have this one. This will give you marks. Okay, that will give you marks. And finally, you'll be getting as such. This the conversion as mentioned earlier just now, yeah? The conversion. Excuse me. Okay, so you have as such. Again, you do that one, you have the result. So what happened to the shape now? Again, construct the just copy vector diagram. So if you look at my solution, where do you find my solution is wrong? Could anyone check that is correct or not? Check correct or not. So you can do your correction in your books. It is correct or not? It is correct or not? Anyone?
Checking, Doctor.
Because this one is all your units, all the units. This one is coming from the omega. This one is coming from this one. Okay, check, you can check, yeah. So the effect now, as you construct the effect, you found that okay, this one the omega, this one is, this one be descending, ascending pointing to you, descending pointing the other way. So you will have this one. Just now what you have for the equation, it tells us that the ascending or descending, this one is ascending. So you go back to this one, ascending, what does it mean? Ascending is mean that will be here. And the thumb be pointing to you, you will have as such. Or this one is 2D, this one 3D, this one is ascending. This one is spin, then you have the active. And this is our concern again, your effects. You take this one, put it on the ship. This one, put it on the ship. Okay, so what happened to this ship now? You do this one, you have the ship will be what? To comply the rotation. So you have one force here, you have another force here. And it seems that the ship will be tends to push toward right side. Okay, and finally, you calculated this one earlier. Remember, calculate only one, and you put it this one as pi given as the precession. You put it in the equation, you'll be getting as such. This is the first time you get this one. You get so huge number, isn't it? It's about what? If you look, if I can cancel this one, you have about 1,492.3 kilonewton, equivalent to 1.4 mega Newton meter. That's so huge. But when you construct this one, you found that this omega and the position will be moving or perhaps in the same direction. Look at this one. This one is omega. When you're rotating clockwise, for example, from stern, yeah. So this one will be clockwise. The other one will be counterclockwise. So it doesn't matter. So you have I dot spin precession. So equal to 0. Just put it equal to 0. So then the reason will be since, put it as sin, this omega is what? This omega, if you put the scan, this one will be pointing that one. So this omega parallel to the precession. And prove by what? Prove by I cos I equal to 0. Okay, and you found that if the rotating counterclockwise, for example, yeah, for another instant, for example, this is not our concern. The rotating this one, for example, this is not our concern, this one. So as it's rotating that one, so you have this one be the precession. So your graph will be sorry, your just vector diagram will be something like this one. It is the same thing. M still equal to 0, but prove by what? I cross negative I equal to 0. Because this one opposite direction, this one is same direction, so you have the omega, this one the precession. So as what you have this one in your explanation in your book. So here is the results. So I did put here, there's no gyroscopic effects when the ship roll either clockwise or counterclockwise. So the magnitude of the magnitude of couple becoming 0. Okay, we have a couple of minutes. Any question before we move to the next one, to the last one, last of the what do you call it, the special example or special case on the effect gyroscopic couples. Any question? No? Okay, allow me to do the last one, this one. Inshallah, I'll be calculating this one later on, yeah? Example or problem 11 on page 200, inshallah. Okay, what you have here, this one is a land vehicle. This one is very interesting because you experience every day. Every day you will be facing this kind of problems. Not ship, not the aeroplane, isn't it? Okay, now, when we are talking about land vehicle, we are basically talking that, for example, cars, lorries, but not motorcycle, because the motorcycle or perhaps the effect of gyroscopic on the motorcycle is depending on the rider. The rider will keep changing the effect of gyroscopic couple. So it's very difficult for us to define. So that one is not in our scope at the moment. At the moment now we're focusing on all the wheel will be stick on the road. For example, trishaw, yes, or perhaps spider. You know the spider when we have the BMW, one wheel at the rear and two wheel at the front, isn't it? So the spider. I don't know what they call this, the spider. The other one is what perhaps the long vehicle, for example, 12 wheel, for example. So any wheel that stick on the surface, which will not be jeopardized by when it turn to left or turn to right, or climbing or diving. So our example now, or perhaps occasion now, does any vehicle, land vehicle, have a diving and climbing? Yes, it is, but not the actual climbing and not the actual diving. So for example, we have turn to left, correct? We have turn to right. That is so obvious. You don't have the climbing, you don't have the diving, you don't have the climbing. What you do have is while driving, for example, and you hit the puddle. Puddle is a pothole, for example. So when you hit the pothole or you hit a ramp, for example, and you don't grip the steering, you find that the vehicle has tendency to what? To move toward left or to move toward right, or it could be off-roads. And finally, if you don't grab the steering, you have experiencing the turtles of the vehicles. So that's something like that, yeah. Okay, I'm going to explain to you how does it goes, bit by bit. Okay, because this is so different compared to the ship and also airplane and also the motor. Because in ship, for example, you have only one device or perhaps one body to ensure that the ship move from one station to another station. Same thing as aeroplane. You only have a one machine or one engine to ensure that it will be flying, isn't it? But not in vehicle. Vehicle have two things to do. Two things that keep rotating on operation. For example, the engine be operating, running with certain speed. But if you don't engage the gear, the vehicle will not move, isn't it? The vehicle will not move. So we have two things now. One will be the inertia from the engine. The other one is the inertia of the vehicles. So to ensure this occurs, so because anything that happen to the vehicle, whether you turn to left and to right, is depending on the wind. So our precession is always on the wheel. Remember that our precession is always on the wheel. It is not on the engine. Because why? Because the wheel is stick on the ground and it will be maneuvering, turn to left and turn to right, or perhaps hit a pothole or puddle and also hit a ramp, for example. So remember that the precession is always on the wheel. That is one thing. So when you're viewing the car, for example, you have one will be from the rear end and also from the front end to ensure that the car move forward or toward. So the wheel will be rotating that way. So that will be the precession. Sorry, that will be the spin. That will be the spin will be on the wheel. The spin will be on the wheel. Remember that, yeah? Precession will be depending on turn to left or turn to right. Okay? So, but when you are in front of the vehicle, for example, and the vehicle toward you, isn't it? The vehicle towards, so you will be rotating that way, isn't it? You'll be rotating that way. So the spin will be pointing that way. So it depending on where you view the vehicles. Okay, but very much easy if you view from rear, for example, because you'll be having this one. Move forward, spin. Move to you, spin. So we are not going to talk about when the vehicle on moving backward. No. The reason is when moving forward, it's very difficult for us to take a left turn or right side, and very seldom occurring in our daily life while you are driving. Basically moving forwards, yeah. Okay, so that's one thing. The other thing, when you have a vehicle, for example, I'm not good in drawings, yeah. So don't if you look at my drawing is so bad, please do not do not fool me or do not tease me, yeah. So for example, these are vehicles from top view. As my drawing is not good, that's why I prepare my notes as best as possible. So is the vehicle, if you look at from plan view, yeah, the vehicle has tendency to move or to have this one will be one right turn, correct? This one we have left turn, isn't it? Correct, not left turn. So when this one we turn to left turn, for example, it's left turn, for example. So this one become inner wheel. This one become outer wheel. You have to understand this one. Inner wheel, outer wheel for both. But when you make a right turn, for example, you will change. This one become inner wheel. This one become inner wheel. This one, yeah. Now it become inner wheel. This one become outer wheel. So the inner wheel and outer wheel position will be keep changing depending on where you drive. Okay, remember that, yeah. The inner wheel and outer wheel will not stick as it is. It depending on turn to left or turn to right. Okay, of course, yeah. Again, it's also depending on where you view. If you view from here, for example, you have it from here, and it turn to left, for example, so it'll be the other way around. This one become inner wheel, this will be outer wheel. So it depends on where you view. I'm saying that if I'm viewing from rear. Okay, so now the next one will be we are going to have this one. So in general, when you are talking about vehicles, yeah, we have a couple of things that you have to understand. One with the effect of this whole thing. You have three things or three effects. One be due to the weights. The other one is due to curvature, which we call as centrifugal force, and finally is due to gyroscopic. But to simplify the whole thing, to make sure that the calculation is easy as possible, we are assuming that this CG fall at center. This one fall at center. Basically, it is not. In the actual vehicle, the CG will not fall at center. Some vehicle fall at 1/3 and 2/3, for example. So it depending on what type of vehicle. So in here, we are seeing that the CG will fall at center. Okay, as we are decided to to assume that the CG for the center, so every wheel will carry the same load, isn't it? Because we already decided that the CG will fall the center, so every wheel will carry the same load, even though in the actual one it is not. Remember that, yeah. In the actual one it's not. If you have a background from the automotive student, yeah, SKMV, for example, this one is not, this assumption is not correct. The assumption must be based on the actual vehicle. For example, you're talking about Honda, for example. Honda is 1/3 and 2/3, so the CG will be 1/3 from the front. That one will be so in that manner the wheel will not have the same width, isn't it? So that is what you found when you keep changing, or when you want to change the bearing in the exam, the mechanic will ask you, this one front wheel or a rear wheel, or front wheel, because different, side of wheel will have a different type of bearing. So in here, we assume that the CG will fall the center, so you divide it by 4. Why do you divide by 4? Because you have 4 wheel. You are talking about 12 wheel, for example, you divide it by 12, for example. You are talking about trishaw, you have 3 wheel divided by 3. So it will divide it by number of wheel. Okay. This one is just to ensure with you that the parameter, all parameter being used here, yeah. Mass, this is the radius of curvature when you have turn to left and turn right. This one is the radius of wheel, because you need to know what the speed of the wheel later on. And this h will be the distance from the levels from the surface to the center of, or from the center of gravity of the vehicles. This one. That is why you found that the Formula One, for example, will have very small h to ensure that the vehicle will not easily turn turtle while driving so fast or with high speeds. This h will be the distance between one wheel to another wheel, or axials. Yeah. The IW representing the mass moment inertia of the wheel. The omega W is the speed of the wheel. The IE, E for the engine, W for the wheel. Yeah. For the I engine, and this one omega EOD, omega for the engines. And of course, because you have the wheel and engine, then finally you have the gear ratio. You have the gear ratio. Okay, and this one is not this one is not strained with you. This one is basically coming from the linear velocity, which the velocity coming from the kinematic analysis. Yeah, this is the consideration. As I mentioned earlier just now, you have weights of vehicle, and we are assuming the CG for the center. We have the precession. The precession means turn to the left and to the right. You have the centrifugal effect when this one centrifugal effect. Remember, yeah, centrifugal effect meant when the vehicle make a circle, for example, you will have the F centrifugal. Some call centripetal, some call centrifugal. It is the same. Centripetal is basically when you have the radius with constant radius. Centripetal, when centrifugal, the radius is keep changing, but basically the same. But you have the FC and the other one, the FN. Remember this one, FN, you learn this one in your dynamics. Yeah? And then we have the vehicle stability. The vehicle stability basically that while turn to left or turn to right, you have to ensure that all wheel will always stick on the ground. None of the wheel will be leaving the ground in such way make the vehicle, turn turtle, for example, yeah, or off-road, for example. This one, as I mentioned earlier, divided by 4. Why divided by 4? Because we have 4 wheel, we are talking about motor cars, isn't it? Okay, the NU is pointing downward, class. This one is pointing downward because why? This one is due to weight. But remember, you have this one divided by 4 for all this one divided by 4, isn't it? This one is due on CG. This one is on CG. For each wheel, you have this one on each wheel. But remember, this one is wheel from road. This one is the reaction from road to wheel. Understand me or not? This one is from wheel to road. This one is from road to wheel. The reason is why, because the surface is the hard surface. When you hit the hard surface, it will be hitting back. But obviously, because it is road, it will not hitting back. But you will feel the pain. For example, yeah, you box or you hit wall. You hit the hard wall. The wall will not hit you back, but you will feel the pain. The pain will be the reaction due to the hard wall. Same thing here. Okay, same thing here. This one is from the vehicle to the road. This one from road to the vehicles, and this one you cannot see. Yeah, this one you can see. This one you can only calculate. This one you can see. You can see if you do the simulation, for example, you know that how much load on the roads. Okay, this one centrifugal, as I mentioned earlier. We have the FC when turn to right or turn to left. This one will always outward. This one is the reaction with FN. I think this one you've done in dynamic. This one is active, this one is reactive. And the reactive is also always pointing inward of your radius of gyration. Sorry, radius of curvature. Radius of curvature. Okay, look at the equation now. why we divided by 2? It's not divided by 4 anymore. Why? Could anyone explain to me why we divided by 2? Do not memorize this one, yeah? It's very difficult when you want to memorize this one. I will explain to you how do you get the results of the equation. Why we divided by 2 this one, class? Why? This one, yes, correct. We divided by 4 because we have 4 wheel. If you have 6 wheel, we have 14 wheel, you divide the number of wheel. This one, why divided by 2? Anyone?
2 row.
Yes,
Moment
2.
of
Or we call it 2 axial. The front one on the rear one. Okay, the front have another one. RC divided by 2, RC divided by 2. Okay. So if you are talking about 16 wheel, you have to divide it by what? 16 wheel. You have to divide it by number of axial. One axial carry 2 wheels. And again, we are assuming what? We are assuming the same axial carry the same weight. Because why? CG fall at center. Okay, but if you design the actual thing, it is not, yeah? This one is for the simplification of our calculation. Okay, this one, how do you get the result? This one, do not memorize this one. It's very difficult for you to memorize. Look at this simple thing. This one is not very difficult. This one also not very difficult. This one you convert it. Remember this one, you convert it from AN. AN is basically omega square R, isn't it? This omega is not the omega of the engine. It's basically the omega of the precession. We change this one to become precession. The R, this one is the big R, is the radius of curvature. And this one can also be in the other form. The velocity at that particular instant divided the radius of curvature. But remember, yeah, you need to change this one from the edge. You have edge here. From edge to the levels. That is why you have this one. So the MC that you calculated is the FC multiplied by H. The moment, isn't it? Force multiplied by the H. And what is the FC? You go back to this one. Then you have to divide it by R. Okay, but remember, you have you have 4 wheel, 2 axle. That's why you have to divide it by 2. So please do not memorize this one. You have to understand. If you have, for example, 16 wheel, you have to divide it by 8. So it depending on number of axial. It's not depending on number of wheel, depending on number of axial. This one, yes, depending on number of wheel. This one, no. This one depending on number of axial. Okay. Okay, this one is no big deal. This one, yeah, is no big deal. This one is no big deal. Look at it, this one. As I mentioned earlier, you have 2 initial just now. One initial coming from the wheel, the other initial coming from the engine. And it is very obvious that your vehicle only one engine. So you have this one. The M engine, I engine, precession, omega engine. This one is depending of number of wheel. If you are 16 wheel, you have to divide it by 16. Okay, this one for 4 wheel, divided by 4 because we are focusing on motor cars or cars here. Again, this one we use again in the gear ratio, applying here omega O by omega I or output by input, omega wheel by omega engine. And again, remember there is no number of teeth here. So the number of teeth, the gear ratio will be depending on the velocity of the vehicle and also the velocity of the engine, or perhaps in other words, is the tachometer and also the speedometer. This one is the speedometer. This one is the tachometer when you have in your dashboards. Dashboards. Okay. This one in that your dashboard you have 2 meters to provide you the present gear ratio at that particular speeds. Yeah. Okay. Look at the gyroscopic effects. As I mentioned earlier, because you have 2 things to two body to rotate. Yeah? One with the wheel, the other one is the engine. So you have this equation, and the equation provide you plus minus. Why plus minus? I will explain to you later. This one plus minus. So the plus minus is depending on the position of the engine. For example, you give plus because you found that the wheel and the engine rotating in the same direction. How do you know? The equation will provide you the information. For example, look at here. For example, yeah. I want to expose to you this one. Look at here. They mention about what? They mention about the engine axis is parallel to the rear axle and the crankshaft is rotated in the same sense of the road wheel. So what does this mean? M total is equal to the M wheel plus M engine. Okay, so this one same sense means same direction. Okay, if this one will be opposite direction, we have to put negative. So it depending on the parameter, the given parameter. How do you know? We provide you in the information, in the equation. But typically, if you're talking about impractical, yeah, you found that most of the Japanese car, Malaysian car will have same direction because the position for the engine will be same or parallel with the axial. If you don't believe me, you open up your bonnet, you look at the engine. Okay, but sorry, you look at the boot, you look at the engine. If you go back, if you go to the continental car or European car, namely like Audi, Mercedes, BMW, for example, you found that the engine will be located horizontal, sorry, transverse and also uh, transverse and longitudinal. It's a perpendicular. So as a perpendicular, you found it, the direction of engine and the speed on the wheel will not be the same. So you'll be getting negative. Okay. So don't bother about that one. There will be no sense of mentioning what type of engine, yeah, or type of car. Mentioning of the direction of the engine and also the wheels. I just give you exposure on basically or normally what type of car on running the same or different direction of the engine and also wheel. Yeah. So this one plus and minus depending. So we have as such, you have as such. Then you have turn to left or turn to right as usual. You also have to diving. It's not basic diving when the vehicle hit a puddle or pothole or hit a hump climbing. Okay, that's about it. The information. I think you have to understand. The rest will be basically the same. Okay, let's assume one example here. Yeah, one example to construct the free body. Sorry, to construct the gyroscopic vector diagram. Look at here. Make a left turn, for example. Okay, left turn. So the vehicle now moving forward. Okay, the vehicle moving forward. You have this one. So this one is the spin, the omega. Let's assume we are viewing from rear. Okay, so this one is spin. Then you have two things, plus or minus, depending on the position of the direction. The position of the rotation of the wheel and also on SO engine. It will provide you. So don't bother about this one. So you have this one and this one. So think about this one. Yeah. Okay. Now, when the vehicle now make a left turn, this one the left turn on me, this one the right turn also for me. Yeah. For you, it's different case. If you look at the screen, this one left turn is pointing upward. So pointing upward. Then you want to define where be the couple, you make a right hand triangle rule. This one the spin, this one will be the precession, then will be the couple pointing to you, isn't it? So the couple pointing to you will have a dot product, dot sign, or you will have as this one M active, and this one the M reactive. Okay, this one is M reactive, this is our concern. But this one, look at here very careful, class. I'm going to explain this one. Look at here. So the M reactive is occurring on the wheel and engine. Likewise, what you have in the aeroplane and also on the ship. Same thing, engine and wheel. This one be occurring on one bearing and vehicle, the body. Look at here, the body. So you have to look the question very careful. If the question asking about what happened to the wheel, you have to look for this one. So you don't need to look for the reaction. But if the question asking me what will be the bearing reaction, then you have to look for this one. So it depending on what type of question you face. Okay, it is not exactly as what we did in the what do you call it, in the aircraft or on the vehicle. Naval ship. Yeah, it is quite different here. A bit different here. Okay, so you have this one. So again, yeah, when you're talking about this one on engine and on wheel, yeah, you want to ensure, typically the question will ask you which will have a tendency to leave the ground. So you have to look for the active. It's not reactive because this is occurring on the wheel. Okay, occurring on the wheel. So the wheel will be leaving the ground, isn't it? Or tend to leave the ground, so it will off of the road or run off the roads. I do explain here a bit regarding what is the reactive and what is the active here. For the reactive here, you found that you have this FG, this one all reactive pointing upward, and because this one on wheel, this one also the same thing, also pointing upward. Okay, this one is when on vehicles. So what would be the force on vehicles, on bearing, on bearing, for example? So you will have some. So finally, or perhaps in conclusion, you have to read the equation very, very careful. It's not as what we have earlier. Okay, now let's not pick up another one. I'm not going to explain this one. Yeah, I explain this one a bit confusing. What I intend to do now is to look at this one conclusion. Then I will go one in detail. Look at here. This one is inner wheel. Why inner wheel? Remember, you turn to left. Turn to left. This one become left inner wheel. This one become outer wheel. So these are all forces reaction. These are all the forces, all pointing upward. This one is two pointing downward, one pointing upward. Okay. So in conclusion, you found that this one had tendency to leave the ground because this one from the ground they push the wheel up. But this one, to ensure that the vehicle will stick on the ground, you have to use this equation for stability. I'm explaining this one. In other words, this equation will be defined. So you have these two, you add up together, must be equal to this one. That will make the thing will be move. It will be stick on ground. Or in conclusion, you will find as this one, stability. You might not be, fully understand because you don't face any example yet. After this one, I'm going to explain in example. We have a couple of minutes before we end our session. And this one, you done this one in dynamic. I purposely do this one because I want to continue thing that you learn in dynamics. But the only difference now, when you do in dynamic calculation, you cannot tell which will have to leave the ground. You can calculate on the magnitude, but you can't tell which wheel, inner wheel or outer wheel, has a tendency to leave the ground. That is the only difference, because in calculating the thing that you learn in dynamic is not to point on the 3D or perhaps in 3D, three dimension of a problem. We are basically dealing with the 2-dimension problems. Okay, this one, you done this one in dynamics, no big deal. You can do this one, but they're very difficult to look at which will have to leave the. For example, this one, turn to right, for example, isn't it? Turn to right from rear, yeah. This one from rear. This one from rear, isn't it? Turn to right. Correct. This one is right. So which wheel? Inner wheel has tendency to leave the ground. This one is coming to you. So you have the outer wheel have tendency to leave the ground. Don't bother with this guy. This one play around with the position. Yeah, no. Focus on what happened to the structure or to the body. Or perhaps the possibility of turn turtle when you cannot control the whole thing or you keep speeding up, then the vehicle will make a very severe condition. This is the actual things. Yeah, this is the actual thing. Look at here. This one is not the actual thing. This one is I mean, not the actual thing, meaning that this MG fall at center. This one fall at center. That is why you found that all will leave the ground. But look at here, you found it in the actual thing. You have the rear wheel leave the ground, but not the front wheel. The reason is why the G is not fall at center. Same thing here for the BMW. you found that this one have tendency to leave the ground, not the front wheel, because the MG again is not at the center. Same thing this one for the Honda, for example. This one already leave the ground, but not the other way. Because why? Because it's not the a center. But what we assume here, the CG, this one fall at center. This is why you have to explain the both wheel are leaving the grounds. Look at here, another example which is very obvious here. You have a 16 wheel, for example, 2, 4, 6, 8, 10, 12, 14, isn't it? 6, 12, yeah, 12, yeah. You found it, isn't it? This one is leave the ground, but not this one. The reason is why, because the MG is not in at the center. Same thing as this one. Okay, these are all figure to share with you that whatever you calculate this one is not the actual thing occurring in the practicals or in the real life situation, because we make assumption that the CG fall at center. Okay, so I think we come to end. I will open the equation before we move to the example. So when I meet you again, inshallah, tomorrow morning, I'm going to explain this one in detail, and I'm going to give all reason why the calculation have been done here. This one, yeah, you have this one. I'm going to explain all the numbers here. How do I get the numbers? I mean the calculation, yeah. Then you can do on your own. Then you can start doing the assignment. Of course, at this time, you can start dividing all numbers of the problem within among your friends or among your group members. Yeah. Okay. Any question?
No, doctor.
Open to question. We already completed the whole thing of the gyroscopic effect from the rotor to the vehicles. The only I haven't touched is this one, yeah, this solution. Even though if I forget to do this one, you can do on your own because you have the solution with you. I think a couple of example here, but of course I will explain later on, because my aim is to help you in solving this one. It's not to do another time of the solution. I'm going to help you to solve this one, which I think more beneficial rather than explaining things that you have in your hand. This one, for example, this one I think last semester test equation, last semester equation, and talking about the assignment, perhaps next week's or end of this week, I'll be giving you, inshallah, the individual assignment which you have to do on your own and submit the submission also on your own. It is not a group assignment anymore. Any assignment regarding the books is on the group assignments. Okay. Perhaps I can start doing some other example later on when we meet again. Due to our learning schedule, we have to end or we have to finish the whole thing toward the end of weeks on the gyroscopic, because the next coming week we'll start with balancing. In fact, the last lecture on Wednesday, I'm going to look for the introduction for the balancing, which is more, it is all topic basically interesting. Yeah, interesting meaning that as an engineer you have to do this one, you have to know this one, because when you face things that you have a knowledge to basically do the troubleshootings. Okay, any question, class, before we end our session? We have already reached times here. Any question? I think I received a couple of questions regarding if they provide you a shaft without the mass. It simply think that when you have a shaft without mass, let ignore the mass of the shaft, let ignore the eye for the shaft. You take only the direction of shaft, whether clockwise or counterclockwise. Okay, of course they provide you the what these they provide you what? They will provide you the direction of the rotation of the propeller. Okay, if there's no question, I would like to end my session today. Thank you for having me in your times in class. So I really hope that you enjoy my lecture. If you doubt about things that in your book, you can you can bring in class. You can also ask in in person. Yeah. So thank you, class. So I would like to end with Assalamualaikum warahmatullahi wabarakatuh. Hope to see you again in the next lecture. So stay safe, stay healthy, and stay study. So wish you all the best. Thank you, class, and see you again inshallah tomorrow. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, doctor.